not robustness. So I would like to illustrate robustness, first of all, by reducing the complexity of federated learning significantly. And I say I have a federated learning network with a single node, which means I have a machine learning problem. So any requirements for robustness in federated learning implies requirements for machine learning, because machine learning is a special case. And maybe the most simple federated learning or special case machine learning problem is the following. I give you a list of numbers, a sequence of numbers, and you have to estimate the average. Or I also tell you that these numbers are drawn from some probability distribution, and you have to estimate the expectation or the average, the expected value or the mean of this probability distribution. What's the best way to do it? So this is, I would say, the mother of all machine learning problems. You can formulate this as a machine learning problem of learning a single weight parameter or a single parameter of a linear model where the feature is always 1. So a very trivial model, but you can at least capture this mean estimation problem as a machine learning problem. So what's the best way to estimate the mean of the underlying distribution, which you don't know? What would you do? How would you estimate the mean? Yes. Take the median of means. Yeah, any simpler approach? What is your first guess when you have a sequence of 10 numbers and you want to estimate the mean of the underlying probability distribution? Take the average, yes. Yeah, take the sample average. Add up all the numbers and divide by the number of numbers. Is this the best approach? Well, if you're a mathematician, you would ask, what do you mean by best? So if you fully trust the data source and say, these are really exactly with absolute precision, these are realizations, IID, so statistically independent and identically distributed realizations of one underlying probability distribution. And if you say, if you subscribe to this assumption, then the average, I think, is the best estimator in a very strong sense, the best. But there are a lot of assumptions. And that's a key problem in machine learning. You observe data in the wild, like via scrolling around the internet. Like I find those numbers somewhere on a data repository hosted by some Austrian. So who knows if he is or she is trustworthy? And this maybe you should do. I mean, a bit of being careful is good. I mean, if you have no trust at all, I think we would not be able to survive. So we would not be able to live. We need some basic level of trust. But trust is good, but sometimes control is better. And here we can use mathematics. So here we can use, again, mathematics. Use a mathematical model to model our lack of trust. And we say, this Austrian repository there is not really trustworthy. Let's say we cannot be sure if a fraction of 10% of the data points are completely arbitrarily changed. So somebody poisoned the data. So I have marked here 2 data points which are arbitrarily changed. And but nobody tells you which data points have been poisoned. The one who poisons it has great fun in hiding these intentions, in hiding the poisoning. Nobody tells you which one are poisoned. So if we assume now that the data set comes from a regular distribution, comes from an honest data source, but it is manipulated by 10% data points can be changed arbitrarily. And also this poisoned data points can depend on the statistics of the clean data set. So the Austrian cyber criminal, so to say, can analyze the statistical behavior of the clean data set to very carefully, in a very clever way, choose the data points to poison. This is called the adversary setting. this is different from a simpler or more easier setting from the perspective of defense, where somebody can pick randomly, does randomly picking 10% of the data points and changes it randomly. And this randomness doesn't depend at all on the statistics of the clean data set. So it's a bit of a more stupid poisoner from Austria. He just randomly picks 10 data points and randomly changes them. But here we have a more dangerous, a more sinister poisoner who can study the clean data set, analyze it, and somehow anticipate how would the one who estimates the mean use this data set and take this knowledge into account to poison the most detrimental data points. So in this adversary setting, what do you think is the best strategy? It's not taking the mean anymore, I can tell you. What do you think? Intuitively, how would you approach this? When you say, when I give you a sequence of 2, 4, 5, 10 numbers, and I tell you 2 of them are poisoned, what would be your intuitive strategy to estimate the mean of the underlying distribution, true distribution? Yes. Yes. So one very good comment was, a suggestion was to take the outliers into consideration. And this seems reasonable. Just I want to point out that the nasty Austrian poisoner might know this intention, and not touch the outliers. Yes. The mode, yeah. So use some other statistics than the mean, like median or mode. Yes, yes. Also, but still, the poisoner might know this, that this is your strategy. Mhm. Yeah. Yeah, I mean, the only thing they could do with these 2 data points is to make it very different. So to make these 2 poisoned, these 2 red data points very large. But then you would succeed in this outlier detection. So the only way to hide from the outlier, from the outlier aware learner or machine learner, would be to put them not in the outliers, in the middle somewhere. But then they don't hurt so much. So this hints already that actually it's the best approach is to find the outliers, avoid the outliers, and take the mean of the rest. And this is called trimmed mean. The trimmed mean approach. And yeah, I have shown here, included here a reference to a recent paper from 2021, a nice mathematical paper from the Annals of Statistics, where you find a proof that this is optimal. So when you know that a certain percentage, let's say 10% of data points can be poisoned and arbitrary, then the best way is to avoid the top 10% data points, the lower 10% data points, which could be outliers, and take the mean of the rest. This is called trimmed mean, or a variant of the trimmed mean. And it turns out this is the best you can do. And this is different, but this is a different optimal strategy than from what you should do in the lazy poisoner scenario. So the lazy poisoner doesn't carefully pick the data points, but very stupidly just every 10th data point or randomly selects 10 data points, 10% of data points, and changes them randomly without taking into account the distribution of the clean data points. For such a more stupid poisoner, the best defense strategy is using the median, as has already been pointed out. So the median is any value such that the number of data points above this is the same as the number below it. And it turns out that this is much, much more robust than taking the average. Take the median. I mean, you can easily confirm here, for example, if this is the median of this data set, and if you pick any of these data points above and make them arbitrarily large, it doesn't change the median at all. So the median is completely immune to these extreme values. However, it turns out to be suboptimal, to be not optimal, when this poisoner can analyze the clean data set and try to hide behind the actual outliers in the clean data set. There you should use the trimmed mean. Okay, so how is this relevant now for federated learning, this simple problem? Well, this was also one of the main ideas to break down or to reduce federated learning to this regularized or regularization point of view, because this here is nothing. You can rewrite this optimization problem actually as a mean estimation problem for vector valued data points. And that's how you can basically translate or you can guide, you can inform how you chose this or how you modify this in order to have a similar behavior as for this simple mean estimation problem. In particular, it's not too difficult to then get the idea to use not the squared 2 norm, but use only the norm. And this could be motivated by recognizing or by remembering that the median is the solution of this minimization problem. So you can write the median as the minimum absolute error loss, or the minimum average error loss estimator. So this is the same or similar to linear regression, linearly squares regression, except that you use here the absolute value instead of the square of the prediction error. And similar, we can make federated learning more robust if we use the norm, the Euclidean norm, instead of the squared Euclidean norm here in this total variation term. Okay. What could be a disadvantage? So from a robustness perspective, it seems to be not good to use the squared Euclidean norm, and we should rather use the Euclidean norm. Why could it be? What could be a drawback of using this Euclidean norm instead of the squared Euclidean norm? Well, for example, we cannot use gradient descent anymore. This Euclidean norm is a non-differentiable function. So you cannot use the gradient descent algorithm anymore. You must use another algorithm like fed-relax, which might be computationally more costly. So you buy or you must invest more computation to get more robustness. Okay, any questions at this point? Yes. Yes. Yeah. Yes. So the question was how does this translate to non-parametric methods or non-parametric models? Well, in non-parametric models, we don't use the difference between the weight vectors, but we use the difference between the predictions on a test set. And then it depends if we use the square of this difference or the absolute value of the difference between the predictions on the test set. So instead of this W, you have here the output of the trained models. So you would have here the current model at node I applied to some feature vector in the test set. And here you would have the current trained model at node I prime applied to the same data point. And then, of course, the question is, how do you compare this? You need to get a loss function, typically non-negative. So you can either take the square or you can take the absolute value. And from a robustness perspective, it seems to be better to use the absolute value here. Okay, any other questions or comments? So bottom line here is, for robustness, it might be better to use non-differentiable loss functions, like the absolute error loss or the Euclidean norm for vectors. And yeah, you get more robustness, but it's computationally more complex. So I also welcome you to try out, compare this least absolute error regression or Huber regression, it's also known as Huber regression, with least square regression, and fit those models in Python on the same data set and take the time it takes for the computation, and you will see significant differences. So here you need non-smooth optimization methods, which are typically much slower than methods for smooth optimization, like gradient descent, which you can use if you use a squared error here.